In this video, we're going to be developing two different formulas to solve for the maximum height and the range for something that's in projectile motion. Now, you can derive a formula to always find the maximum height and range, but it's important to know where it comes from so you're not using formulas that are just kind of completely out of nowhere. So on the top of the screen, we have 3 acceleration formulas and 1 constant velocity formula. We're going to need a couple of these in order to come up with our formulas. So let's take a look at the one for maximum height first. So a couple main ideas about a projectile that reaches its maximum height is number one, the acceleration due to gravity is always negative 9.8 meters per second squared. The second thing is the final velocity in the y direction is always 0 meters per second. That is the instantaneous velocity at its peak, only going vertically though, but it does have a little bit of horizontal velocity here. And then from there, we could do a couple things. We can take a look at this formula right over here and plug in some information to solve for the delta y. So if we're using this formula over here, on the left side we have vf squared, so which is 0 squared, and 0 squared is just going to be 0. And that equals the initial velocity squared plus 2 times a, which is acceleration due to gravity, and then we're going to find our delta y. So if we rearrange some of that information, we're going to end up with negative vi squared if you subtract that from both sides, and then you can divide both sides by 2 times a. Now, what you can do in addition to that is a couple things. Since we know that the acceleration due to gravity is negative 9.8, if we're talking about something that is neglecting air resistance, this is always going to be 2 times negative 9.8 on the bottom, which is always going to be negative 19.6. So then we would have vi squared over 19.6. And then we are going to drop the negative because the negative from this negative 9.8 and the negative in front of that vi squared are going to cancel each other out. Okay. In addition to that, we can also do one more thing. Our vi right here stems from the vi from our original velocity. So we have a horizontal and vertical velocity that is broken up from our main initial velocity of our projectile. Now, in order to get the y component, we're going to have to do the original initial velocity times the sine of the angle. That's going to be our vi over here because we're working in the vertical direction if we're solving for the max height. So we can go ahead and simplify this one more time, and then we can call it vi squared sine squared of theta all over 19.6. And that gives us our delta y, which is our maximum height. So once you've derived this formula, all you really need is the initial velocity right over here, along with the launch angle, the angle above the horizontal. And once you plug those two numbers in, you can go ahead and solve for your maximum height. All right, so let's go ahead and clear a little bit of space and then develop our maximum range formula. So the next thing we're going to do is derive an expression for delta x. So if we take our v equals delta x over t formula and rearrange it, it is delta x equals v over t. And how we get the horizontal component of the velocity is we take the vi and multiply it by the cosine of theta. So I'm going to go ahead and change that already. And then we have a t right there. Now, what we want to do is we're going to substitute out that t. And the way we're going to do that is we're going to take our first formula and we're going to solve for t in terms of some other variables. So if we go ahead and cross multiply the t and the t is going to switch places with the a is going to drop down there, and then it's going to be vf minus vi. Now, one important idea is that when something gets tossed up with a certain vertical initial velocity, it's going to come down and have the exact same velocity as the initial velocity, but with a different sign, which means that um, negative VI equals VF, or vice versa, negative VF equals VI. So we're going to take out this VF and substitute out for a negative VI, which is going to leave us with T equals negative 2 VI all over A, which I'm going to replace with G. Now, G is negative 9.8, so we're just going to take the negative from the G, and then that's going to cancel out the negative in front of the 2I, and then G is just going to be positive 9.8. And then this VI right here, because it is connected to a vertical component of the projectile, this VI is going to be VI sine of theta. So then once we solve for time, the final expression for time is going to be T equals 2 VI sine of theta over G. We're going to take this entire expression over here, and then we're going to substitute that in for the T right over here. So when we do that, it's going to look like this. It's going to be delta x equals VI squared because of this VI and this VI over here times 2 cosine theta sine theta. And that's all over G. Now, there is a trig identity that you can also apply in this case, where 2 cosine theta sine theta is equivalent to sine of 2 theta. Okay, so in order to simplify it a bit, if you use that trig identity, you can swap in the 2 cosine theta sine theta for sine of 2 theta, and then your final expression is delta x equals the initial velocity squared times the sine of 2 theta, and that is all over G. So that is your final formula to find the range of a projectile as long as it is landing at the same level that it was launched at. All you really need is, again, just this original initial velocity, and then the theta, which is the angle above the horizontal it was launched at. And then once you have those two things, you go ahead and plug into that formula, and you're going to find your delta x. So I hope that was helpful in helping you understand the derivation of those two formulas, and you can go ahead and use those to simplify the calculation process for finding maximum height and the range. So thank you very much for watching and listening.